Hi everyone again. Welcome to my talk on data poisoning, visualization using graphs and networks. I'm currently interested in the intersection of network science and cybersecurity, which is what we will look at today. My goal with this project was, what if we could visualize the data poisoning vulnerability in action if we visualize the graphical data that can be formulated from training data used to train LLMs. Machine learning models have become increasingly integral to software applications, so they face increased risks from adversarial attacks as a result. So what if we could visualize that training data using graphs, and then what if we could compare the healthy data versus the adversarial poison data? So today we will go further into that concept of data representation and how attacks can modify or poison data within networks. So as a quick intro, here's who I am and a broad representation of my research interests. I am a security researcher and a PhD student at Dartmouth College in the United States. A few of my research interests include binary analysis, specifically exploring graph theory, machine learning, and supply chain related security. So what is data poisoning? Data poisoning is a well-known machine learning vulnerability. As defined by OWASP, data poisoning is an attack that occurs when an attacker manipulates training data to cause the machine learning model to behave in some undesirable way. Data poisoning occurs by altering data by three methods: addition, modification, or deletion of data. Interestingly, addition can also mean the injection of data, but injection attacks, as we know, do not always mean adding data. To understand data poisoning, we should first look to understand machine learning. So most of us understand how machine learning works at a simple level, but here's a kind of like a quick overview of what it is. It's a method of teaching computers to recognize patterns and make predictions from data without being explicitly programmed for each specific task. So algorithms learn from examples or trained data to identify patterns, and once trained, models can make predictions on new and unseen data. There are also three main types of learning. So supervised learning, which is learning with labeled examples. Unsupervised learning, which is finding hidden patterns. And reinforcement learning, or learning through trial and error. Machine learning powers like a lot of applications that we use, like recommendation systems, image recognition, language recognition, and language translation, in addition to everyone's favorite LLMs. So how does data poisoning fit into all of this? Here I changed the diagram a little bit, and the model reflects poison data. Poison data goes into training data via some attack vector. The machine learning algorithm processes this data, and then the training model is compromised. And what this all leads to is biased output from the model, and ultimately, the model doesn't fit the intended context of its stated purpose. Moving forward, I wanted to give some examples of data poisoning that we have all experienced recently in the media. But first, how many of you remember who this is? So this is Tay from 2016, actually. So this was a Microsoft chatbot that was released on Twitter. And Tay was designed to pick up our language and syntax via interactions with real people on Twitter. Long story short, within a few hours of launching, it started repeating vulgar and hateful language. The chatbot was intended originally to be like a fun conversational agent, but after training on bad data, it became adversarial, tweeting hateful language, which was the opposite of its original intent. As malicious language was injected into the model, this is an example of a large-scale data poisoning vulnerability. But more recently, a more recent example of data poisoning that blew up recently on Twitter, or I suppose I should say X, is Grok suddenly including racist language in its responses. So for those that don't know, Grok is Twitter's AI chatbot integrated into the platform. Grok provides several features, such as being able to function as any other Twitter account, responding when added, and being able to post. It's also possible to chat with it like any other LLM, like ChatGPT or Claude. And earlier this year, Grok went kind of crazy after receiving a system update, which you can see here, during which it called itself Mecha Hitler, and similar to today, started tweeting inflammatory content. Reportedly, this was caused due to an update where the chatbot was trained to not shy away from making claims which are politically incorrect as long as they are well substantiated. But both Tay and Grok were compromised by ingesting hateful and extremist content from social media. Both incidents reveal a fundamental challenge in AI development. When chatbots are designed to learn from user interactions or are trained on unfiltered social media data, they can quickly adopt the same extreme and offensive content that they encounter. The key difference is that Tay's corruption came from coordinated trolling attacks exploiting its learning mechanism, while Grok's issues appear to stem from a combination of its training data from Twitter and also intentional loosening of content restrictions. So to give more context to data poisoning, I want to quickly talk about the 2017 BadNets paper, which introduced the concept of data poisoning as we understand it. Essentially, BadNets are maliciously trained neural networks that perform normally on regular inputs, but misbehave on specific attacker-chosen trigger inputs. Training deep learning models is very time expensive and compute heavy. So naturally, people would outsource to cloud providers or just download pre-trained models and fine-tune them. As a result, the authors created BadNets that will pass all your chosen validation tests, but they have hidden backdoors that activate when seeing a certain trigger. So this is their most compelling example in the paper. They created a traffic sign classifier for autonomous vehicles. On regular stop signs, it works perfectly fine, like correctly identifying them as stop signs. But if you put a simple yellow post-it note on the stop sign, the network suddenly thinks it's a speed limit sign. So imagine like an autonomous car just driving in the wild. It would just like drive right through into an intersection instead of stopping. So what makes this dangerous is how stealthy these attacks are. The backdoor network performs just as well as a legitimate one on clean data. So there's no drop in accuracy or architectural change. It's just that you would only be able to test this with the exact trigger that the attacker would use. So you would only be able to catch this specifically using post-it notes. Ultimately, within all these stories, the common trend we see is that data poisoning is extremely vague and unpredictable and benefits from some kind of visualization to grasp some understanding of its central idea. So I want to get into the concept of data provenance. Data provenance is the concept of a history of a particular data set. So what has changed from set P, or set Q and set R in this case, and what is that change? You can kind of think of it as a diff function from your favorite programming language, or even when you upload to a GitHub repository, like what lines of code has changed and which lines of code remain the same. What I want to illustrate is that we can also track these sorts of changes in our databases to use for threat detection. And this is ultimately what I wanted to observe with data poisoning. So what's the difference between poisoning data within a graph or a network? But before we get into applied data poisoning, what is network science or graph theory? Various systems and their subsequent data sets can be defined by networks, such as the World Wide Web, the nervous system, and social networks. Behind every complex system is a network that defines interactions between its components. Mathematically, graphs are representations of such networks. Graphs consist of objects called nodes and edges that would connect these nodes. And almost anything can be defined in some way by a graph or a network. Networks are powerful tools for prediction, but are only as accurate and stable as their data sources. Paths, or a sequence of nodes connected to one another by edges, allow us to make predictions or implications about the underlying data. Analysis of networks also leads us to some interesting statistics, such as edge multiplicity, or multiple edges sharing the same nodes. Edge multiplicity represents the intensity of certain connections within a network, which can be visually shown with thicker lines stretching between nodes. Conversely, sparser lines mean less edges between nodes. Networks help us represent important information, but they can also, as a result, visualize training data for machine learning. All of this vital information should be protected, as tampered networks and data can have cascading results. Training data can be obtained through attack vectors. So for example, private data sets can be infiltrated through insider threats or sophisticated attacks, and public data sets and repositories are prone to data injection attacks. With public data sets, poison data can proliferate into other models and applications that rely on these public data sets. Ultimately, the goal with network visualization is comparing the before and after results of poisoned and cleaned networks to help determine the presence of data poisoning. Gephi is a network visualization and analysis tool used as a desktop application. And the reason why I chose to talk about it today is because it inspired my open source tool that I will be presenting. But to use Gephi, one can upload a spreadsheet with nodes and a corresponding sheet with edges. It is also possible to build your own network by adding nodes and edges and customizing its appearance. It is also open source and includes many different algorithms that help visualize different types of information. In addition, it runs network analysis calculations that provide metrics such as degree distribution and modularity. Since you can also run multiple tabs in a single workspace, Gephi provides an easy way to compare healthy and tampered data in the same workspace. With this tool, I want to go into GraphLeak now. So my goal with GraphLeak is that I wanted to build a simplified Gephi as something one could just run in a browser and easily drop in network files without the learning curve of Gephi. I will always advocate for Gephi usage, but to me it's important that visualization applications are intuitive, especially when it is for a vulnerability application. The tool I developed is called GraphLeak, and it is open source. With GraphLeak, one can just simply upload, poison, and analyze and compare graphs side by side. So you have full control over which nodes you would like to poison, and I also created statistical risk analysis within the compare feature and added some algorithm layouts. This tool also happens to be on my GitHub. So why is statistical analysis important? We use it to give some rough estimate of risk. These risk ratings were not chosen arbitrarily. 10% is the rough amount of poisoned nodes or poisoned data points needed to alter data into noticeably changing the model according to literature in their area, which I have cited on this slide. However, to caveat this accepted statement, in 2016 a paper came out where even less than 10% is enough to find some visible changes in the model. And this percentage was further proven in the BadNets paper mentioned earlier. In fact, there are many papers, even several that came out recently, which consistently prove that 10% or even lower is enough to poison a model. In BadNets, the attack would succeed even if the backdoored image samples represented only 10% of the training data set. So the 10% number is significant to us, but it does not diminish a data poisoning attack looking at less than 10% of the training set. So here's a quick rundown of all the features of GraphLeak. First, you can import CSV data, so typically an Excel spreadsheet. It will take a column of nodes and a column of edges. And then there's multiple tabs for multiple graphs that you can use, which will then translate into the comparison mode. Then on the left, you have graph statistics, such as nodes and amount of edges, which will be important when comparing the two graphs. And then you can also poison the graph, so you can click on nodes fairly easily, and then either delete them, or you can also add nodes to the graph when you specify an edge. And then I have a few algorithms on the left, which I will get into in a moment. So here's a better, perhaps more clear view of the tool. So all of these nodes connect to each other in a network. And also here are the algorithms. These three graphs are all the same. They all contain the same data, the same amount of nodes and edges. On the left, you see a force-directed graph. So these graphs are great for representing clusters and relationships. Social networks are great as force-directed graphs since you can see the formation of various relationships and how they are connected. In the middle, you see a circle graph, which is great if you want to emphasize the equality of relationships. So one node does not have a different meaning than another node, and it is visually better for reducing clutter. Finally, grids are great if you have very large networks, so like thousands of nodes where maybe things like spatial relationships matter. So for example, floor plans or architectural diagrams. And then we'll get into the demo next. So I uploaded a graph in a separate window. And this is just a 7-node graph with 12 edges connecting this small social network. Here I also switch between the layout algorithm. So this is a circle graph, and that's a grid. But for this, we're going to use a force-directed graph. So first, I will add a node. Since this is a social network, pretty simply consisting of names, I'm going to add my name to this social network. And then I will add an edge, connecting myself to this network, which is already poisoning this network as a result. Then I uploaded the same graph to compare the two graphs. Since I just added myself, there's not really that much of a difference between 7 and 8 nodes, so the risk rating is a low. But we'll poison a few more, and we'll see the risk rating jump. So I deleted myself, and I will also delete others. And the graph becomes smaller, and the risk rating jumps as a result. And when you delete more than half of the graph, then the risk rating jumps to a high. So what I showed you is data poisoning in a social network, but I wanted to go more into the graph comparison of the machine learning model now. I want to demonstrate that the poisoning effects of a network line up with those in a machine learning model, training model, which I will go into next. We will poison the MNIST dataset, which is a standard binary classification. Is this the correct number training dataset? So this dataset has an error rate of just 0.8%, which is why it is so nice to experiment with specifically data poisoning. GraphLeak takes in many types of network data, so it's not just an app solely for machine learning models, but for our demo purposes, we are going to use binary classification training data, which is simply sorting things into exactly two categories, true or false, sort of like yes or no questions. In my training case, I'm asking the question to the machine learning model, is this number correct? So I will show you in a moment what that looks like with Jupyter notebooks. And I use notebooks in this case for the ease of demonstration. So you can kind of see some initial training code. So the MNIST dataset is fairly generic. And we want this initial training to then see how our data changes as it's poisoned. So on the right, you can kind of see what happens when code is compiled. It's just running through the training set and predicting whether it's true or false and spitting it out with just 5 results. Here's the initial prediction for our experiment. So you can pay attention to the result at the bottom, and it's pretty simple, right? So definitely a few incorrect predictions, but mostly correct, and I think we can be okay with that for a model that has trained off of 1,000 numbers. After I had this initial prediction data, I add this back to the training count as a part of that machine learning training cycle, and then we can move on to poisoning again. Now, moving on to GraphLeak, here's what that data looks like in GraphLeak. Now, this may look super simple, but actually there are 1,000 edges all laying on top of each other between the numerical nodes and the true and false nodes. Then in Colab, I poisoned the set just a bit. Out of 1,000 data points, I poisoned just 10 values, so this doesn't really have much of an effect. Most of the numbers remain the same despite poisoning 10 data points. That's about 1% of the total number, so it's unlikely to have a significant effect. Here, I poisoned 30 rather than 10 nodes. Again, maybe a slightly bigger difference, but not a big change. Again, the graph doesn't change all that much either. It's just edges and nodes stacked up on each other. However, you might notice a slight visual change of the lines becoming thinner because of the lack of edge multiplicity. Now we can poison all ones possible, so all ones become 4s now. And here are the results. No ones at all, just replaced by 4. So again, we will look at what that looks like in a graph. And it looks pretty similar, but instead of 12 nodes, there are 11 because one is missing. And here I wanted to compare the two graphs where one has all 1 nodes completely poisoned on the right, while on the left is the original with the normal completion data. Since only 1 node was poisoned off fully, the risk rating is quite low. But if we poison the 2s off as well, then maybe the risk rating will jump. And here we poison in Colab again, poisoning all 2s into 4s. And now all the 2s have been removed effectively, and our risk jumps to a medium. And the node difference is much more significant. So what did that demo show us? Visualizing mathematical differences can show us how data has been tampered in a graphical format, and labeling these data points can tell us exactly how it has changed statistically speaking. GraphLeak was also inspired by the concept of data provenance, which, to recall, is the concept of a history of a particular data set. What I wanted to illustrate is that we can track these sorts of changes in our databases to use for threat detection. And we can also analyze our risk using the comparison mode feature and understand how much of our model has changed. For future features that I would like to implement in GraphLeak, I want to do more statistical analysis. So what else can we learn from numbers of nodes and edges and other statistics? Also, one of my favorite concepts in graph theory is cycles. So what do cycles and direction tell us about graphs as a whole? And then how does that translate into machine learning data? Finally, I would like to integrate GraphLeak into a training model to truly show how an LLM can change over time, beyond poisoning just like a theoretical model. So to quickly recap, we know that private and public datasets can be infiltrated. Whether private or public, datasets can be infiltrated somehow, whether it's through insider threats, sophisticated external attacks, or just regular data injection, which is what I wanted to show here. And I want to most importantly reiterate, our LLM data is trained on private but more frequently public data sets. For this purpose, data must be healthy. So what about solutions to this problem with regards to data poisoning? Private data sets need to be private. What I mean by this is access to private data sets must be restricted, ideally with a passkey. And these users should abide by the principle of least privilege. Users of these private data sets should only be given access that they need for that data set. Also, I propose that this GraphLeak should be used for incident handling, and the modification of data should be monitored and tracked. And through a before and after snapshot, we should be able to see the difference or data provenance of that data. Finally, LLMs need to have guardrails. If you've ever asked ChatGPT or Claude or your favorite LLM a question about cybersecurity, it will tell you certain things, but not others. We can have strategic rules that define what we want AI to train on. The LLM should be intentional, and it should internally check what goes into it as an input, and also what it will output. LLMs have evolved into becoming such a common integration in software applications, so being able to visualize these vulnerabilities that affect the training data and effectively the output will help us understand how to safeguard models for safer software security. So bringing it back to Tay, Grok, and social media, data poisoning is an interesting lens to understand broader societal issues beyond training LLMs. Information is spread on social networks and is being used to train on public opinions. When bad actors intentionally flood these spaces with misinformation, conspiracy theories, or divisive content, they're essentially poisoning the information environment. Tay and Grok show to us that extremism can be normalized within society, and this mirrors how societies can experience shifts in acceptable discourse. When extreme views are amplified systematically, whether by algorithms or organized groups, they can poison the broader conversation, making previously unthinkable positions seem normal or mainstream. Social media algorithms often prioritize engagement, which means often divisive content gets amplified. This creates a feedback loop where training data a society receives is systemically biased towards conflict and extremism. So this is sort of like structural data poisoning that affects human learning and opinion formation. When authoritative sources are deliberately undermined through coordinated attacks, it poisons society's ability to distinguish reliable information from misinformation, sort of like corrupting the labels in our collective training data. Perhaps most concerning is how data poisoning can have long-term effects. So we form our worldviews in poisoned information environments that distort our internalized perspective, kind of like how AI trains on bad data and carries those flaws forward. But there is hope, and active solutions do exist. Content provenance, building off the concept of data provenance, does exist. An example of this is Twitter's community notes, as seen on the right. Efforts like this help users evaluate credibility. Recent developments in AI-generated videos have caused the need for verified and real videos. So blockchain or cryptography-based verification and fingerprinting for images and videos is currently being explored as a means to establish credibility and provenance. The challenge is that many of these solutions face trade-offs, so more aggressive filtering risks censorship, transparency can be exploited by manipulators, and finally, building trust takes time, even with community-based efforts. It's also difficult because poison and data poisoning adapts. If we solve one vector of an attack, we can always find another. Thank you.